Edwin Lundberg, who was my master's student 4 years ago and with whom actually this line of research started. So he made the first basic, most important discoveries on which this research is based. And as Mareike said, please feel free to just shout in if you have a question. If you put it in the chat, I might overlook it in the given minute. So yes, as you feel comfortable. So let me first give you the wider context of this area, of the problematics of the area. And interested in such scenarios, situations that are described here, which the common thing is that we have some team of intelligent agents. These can be robots or they can be drones or other types of intelligent agents. And they have some joint mission. They have to accomplish something together, like they have to remove a dangerous object in a field or rescue people after landslide, or they have to assemble something, or Jana Tumova gave me this example, a team of drones that has to diagnose a problem in a wind turbine. Or for example, you can also apply the concept to concurrent programs where you have a set of concurrent threads that have to achieve something together. So most generally, the problem that we are studying is how to coordinate the actions of a team of intelligent agents so as to achieve some joint objective, some team mission, as some people would put it. And then what we are most interested in is in the concept of knowledge in this context. And knowledge, this concept always arises when the agents do not have full information about what's going on. They might not have full information about the map, for example, where things have to happen, of the building where they are, for example. And this type of limitation is usually called incomplete knowledge. Or they may not have full knowledge because their sensors do not allow them to to see the full state of affairs. And then we talk about imperfect information. For example, because of the landscape or because of the walls in the building, the agents do not see each other. So then we talk about imperfect information. And whenever you have imperfect information, then it becomes important that the agents can either remember what has happened so far and make their strategies based on this, or in some sense extract from what they have observed, extract some sort of representation of the information. This is what I call knowledge about what is the current state of affairs, so that to base their actions upon it. So as I say, so knowledge in this talk, when I talk about knowledge, I will mean some sort of aggregation of abstraction from the observations that an agent maps to some finite representation on which to base their actions. This is similar to automata theory, where the notion of a state in automata theory usually is called to capture the relevant part of the history. This is the term that you would find in the book by Hopcroft and Ullman on automata theory. But this is, of course, a very vague phrase, very vague formulation. So, but what is the relevant part? What should we remember? What should agents remember? So this defines the abstraction. What is the abstraction? How shall this information be represented, structured, and used and updated? So these are questions that we are interested in addressing. Also, when you have multiple agents, it becomes a concept arises that is not only what is if I'm an agent, what is my knowledge about the state of affairs, but it also might be important for me to know, to compute what other agents might know now, possibly know about the current state of affairs. And with this nesting of me knowing what other agents know about yet still other agents, or what I know about the current state of affairs, this nested knowledge is usually called higher order knowledge. And then for us, it's extremely interesting question. The question is, how does it affect? So knowing more, this and nesting deeper this knowledge about the state of affairs, how does it increase our abilities to achieve objectives? So all these very interesting questions lead to this concept of knowledge and strategic ability, the ability for strategies to achieve objectives. And usually I like to quote the ancient Greek philosopher of Epistratus, who has said, "To know is to can." So, so back to the notion of knowledge. By the way, I'm pulling you like there's no such Greek philosopher, but we invented this name. I came when we were thinking of how to call our project. I suggested the name of Epistrat, coming from epistemic strategies. And then Valentin asked me, "Who is Epistrat?" And where we happened to sit in this on this balcony, there on the wall was this voodoo image, and I said, "Well, that's Epistrat." So this is how this story comes. So back to the concept of knowledge. So as I said, knowledge, the knowledge of the agent in general refers to information that is suitably structured to decide on a course of action. And this we could uh, divide this knowledge, we could split into so-called static knowledge, knowledge about the static aspects of the situation, for example, the map of the terrain or of the building. This is the static part. And then we have the dynamic aspect of knowledge. This is the knowledge about the current state of affairs. And I will focus actually on the second aspect here. And then naturally for us, we came to the idea that, or to this concept, to this notion of a strategy that is based on the knowledge. And we naturally call this notion knowledge-based strategy. So a knowledge-based strategy then essentially consists of some way of representing. We need somehow to represent the knowledge about the current state of affairs in a structure. And then this structure would mathematically define what is the knowledge state, the current knowledge state, or what are the possible knowledge states of an agent. And in particular, what is the initial knowledge state? We need to know this and be able to define it mathematically. And then in a knowledge-based strategy, we have a mapping. Each individual action of each agent at any point of time should be uniquely determined by the current knowledge state of that agent. So this mapping from knowledge states to actions, this action mapping is needed in order to talk about the knowledge-based strategy. And finally, we need some mechanism of how to update the knowledge. So from a current knowledge state, and based on what action I make, and based on what I observe during the action and upon completion of the action, from this I should be able to recompute now what is my new knowledge about the state of affairs. So that's what constitutes a knowledge-based strategy, and this is the type of strategies that we are studying, that we're interested in studying. And this notion is very closely related to a notion, the notion of knowledge-based programs that was introduced in the late 90s by Fagin, Moses, Halpern, and Vardy from their famous book, Reasoning About Knowledge. So to make this study concrete, we had to make first some simplifying assumptions before we can really define a mathematical object. And these simplifying assumptions are the following. So first, we assume that the arena or the map is finite, discrete finite, and it's known to the agents. So basically, each agent has their own copy of the map in their hands, so to speak. And we also assume that certain state of affairs are indistinguishable for certain agents due to limitations of the senses. And this notion is the one that gives rise to knowledge. If we didn't have this, then the notion of knowledge would not be interesting. Then we assume that the agents do not observe each other's actions. And I have to say, this we start with these very strong assumptions. It's not we don't claim that these are realistic in any case. No, in many cases these are not realistic, and later we will relax them. But as our starting point for investigation, we take this very restricted case, which we later stepwise relax. And we also assume that the agents cannot communicate with each other. This is a very important restriction. And we also assume that the agents should not know each other's strategies. And uh, this is, for example, important for when we recompute, when an agent recomputes the new knowledge state. This comes into play because assuming that I don't see the actions of my partners, but if I knew their strategies, I could sort of restrict the set of possible actions that they may do, and I would get a more precise knowledge about the next state of affairs if I knew the strategies of the other actions. So initially we will impose all these restrictions, and later uh, uh, re, uh, we will relax them one by one. So essentially, then the idea would be that for the agents to synthesize strategies, we assume then there is a central supervisor that will devise all strategies, individual strategies, one for each agent, and will distribute them among the agents.
I think there's a question here.
Yes.
If the agents cannot observe the actions of other agents and cannot communicate, does not the problem decouple to a set of single agent problems? A question from Joachim.
Uh, but still they want to work as a team. So that's why it's not the same, because they do not play against each other. If they were pitted against each other, then this argument comes into play. But we now consider them as a team. So then it makes it still is it's still we consider a team of agents.
I think
If
there's another one actually from by Georgi. I don't know if you want to ask the question.
I see. Yeah, now that you told me, I see them. Yes, I do. So for me, Yuri, a strategy is a mapping between knowledge states and actions, right? Which is which defines my ongoing behavior. So at each point of time, the strategy will tell me, now do this, now do that, right? So the strategy is for the whole course of the play. Uh, did this answer your question?
Yes, it did. Thank you.
Okay. And okay, so and Joachim seems also to be happy with my answer. Okay, thanks you for your questions. And so now, if we didn't have this last constraint about the strategies, about agents not knowing each other's strategies, then we wouldn't need a central supervisor. Then actually the agents can meet prior to the mission and decide together on a joint who should have what strategy, and then go out in the field and follow the strategies. So, but now after all these agreeing on all these constraints, concretely the mathematical object that on which we will study knowledge and strategy synthesis is a class of games over graphs, which is called multiplayer games of imperfect information against nature. I already said what imperfect information is. Here, the important thing is that we have a team of players that act together to achieve a joint objective, a team mission. We have a joint objective for the team. And this term against nature indicates the following, that everything else, all other agents that there might be in the system, are abstracted away and modeled purely through non-determinism. So we will not explicitly model the actions of the other agents that are our opponent. So everything will be abstracted away into non-determinism. So explicitly, we will only model the agents which constitute our team that we are now interested in to achieve its own, the given team mission, its own team objective. Okay? Any questions, other questions so far? Uh, I'm not. Yes, maybe Yuri. I'm not sure exactly about what 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 this notion that you mentioned. Judging by the terms, it seems to me that probably it's the same. But I don't associate probabilities. It's pure non-deterministic choice of the nature. So maybe this might be a difference with what you call stochastic. Uh, so let's see now a concrete example. This example is due to Edwin. Uh, so let's consider a scenario where we have a team of just two robots, and their mission is to lift a cup of, let's say, acid, and then they have to transport it away from the area. And these robots have an arm each, and they have to grip together the cup simultaneously, and then they need to lift it. But it could happen that the grip is not stable from the very beginning, and then they also have at their disposal the ability to squeeze further. And then, but then they also have to squeeze together, and only after they have a secure grip, then they can lift. And we also assume that the first robot is a new generation robot. It has a sensor actually that can determine, see whether the grip is firm or not, secure or not. Uh, while the second robot is an older generation robot and does not have such a sensor. So this situation can be modeled with this very simple game. This is the game graph with just 4 nodes or locations, as we will call them. The start location, then these two locations, bad or good, corresponding to the robots having a good grip or bad grip, and then depending on whether they have successfully lifted or they have not managed to lift successfully. So for example, if the grip is bad and they try to lift, then the cup will spill and the game, so to say, is lost. Okay, so again, so as you can see from this game model, we assume that the individual actions are coordinated. So we always the transition happens upon joint actions. So each of the agents has to do an action. So when both agents grab, um, then here through this non-determinism that we see, we model this situation that non-deterministically the grip will either be good or bad. So in some sense, you can view it that nature is our opponent, is the opponent of the team, and nature will resolve this non-determinism upon the joint action. And then if the grip is bad, by by both uh, robots squeezing together, they will improve the grip. If they keep squeezing, nothing will change actually, and then they can lift. If they lift, they have succeeded in achieving the mission, the goal. Uh, so now, but I said that the second robot does not have the sensor for whether the grip is secure or not. And this is modeled through this equivalence relation indicated by this dotted line here with index 2, indicating that for the second robot, these two states are indistinguishable. So we put them in one equivalence class for this robot. Any question about this example so far? Yes, yes, Georg. So we assume that the game graph is common knowledge. All the players, all the agents know this, including the instability relations. We assume also that the robot one knows that that robot two is the old model. Okay. So the formal definition then is that we assume that we have a team or grand coalition of n players, uh, designate, yeah, called player one to player n. And the mathematical definition is as you would expect for such a graph-based notion or finite state machine if you want. It's very similar to this notion. So the nodes are here called locations. There's an initial location. Then there's a set of joint actions. And as you see, so we assume that each agent I is given a set sigma I of actions. These are the actions available to this agent. In this particular game, it was the same set, but need not be. Then we have a set of transitions between locations based on joint actions. And then we have a set of joint observations. So these observations are the partitions induced by the indistinguishability relation of that particular player. So each player has an indistinguishability equivalence relation on on the locations, which here we model through the partition induced by this relation. So each of these calligraphic OIs is a partition over the set L. Okay, and these are the joint now observations that the team can make. Any question about this? So let me say, since I'm keeping this at a very high level, let me introduce some important notions over such types of games, over graphs. So first, a play in a game is an infinite sequence of of locations that follows the transition relation, right? That is respects the transition relation, essentially a path in the graph, if you want. And or you could call it that this is a, a play that is consistent with the rules of the game. So if you think, for example, of chess, that because in English, the game of chess and the game played on a particular occasion between two chess players, in English you always call it a game. But for example, in Swedish, it's spel and Partie. In German also it's Partei. Partie, eine Chesspartie is the German term for the game of chess, which is the Spiel. So in English you don't have, you always have the, but yeah, but game theoretically you call it a play to distinguish from the game. It's a concrete execution of the game. And then whether a particular play is won or not is determined by the objective. And most abstractly, an objective uh, corresponds to a set of plays. So a given play is then winning if it is, if and only if it is in this set. But more concretely, usually more intentionally, you would define an objective in some logical way. For example, by a linear time temporal logic, you would define such a set of plays, or in some other ways. A class of objectives that for me is important, that we have mostly focused on, are so-called reachability objectives. And then you would define a reachability objective as a set through a set of observations. And then you would say that the team wins a particular play if at some point it reaches a location which is, the observation is in this set. So it suffices in this case that one of the players can see that the goal is reached, and then we say that the team has won. Okay, and this class of objectives is called observable reachability objectives. Okay, and then a strategy for the team is a collection of individual strategies. Okay, or usually you will see the term profile. So we have a profile of individual strategies, one for each player, and each individual strategy is observation based, in the sense that it is uniquely determines the action of the agent based on what the agent has observed so far. So OI plus is the set of all finite sequences of observations of that agent. And because we allow any observation history, so this is the very general notion of so-called perfect recall strategies. So the action is allowed to be based on the full history of observations that the agent has made so far. Now, if we limit, very strongly limit the strategies only that they're only allowed to depend on the last observation. So then instead of O plus, you just ignore this plus here. So mappings from OI to sigma I, this class of strategies are called memory-less strategies or positional strategies. Okay? And then we say that the strategy profile of a team is winning for that team if and only if every play that results from the players following their individual strategy, every play resulting from this is in the set defined by the objective. Okay, then we say that the strategy is winning for this objective. Any questions about these notions? Okay, so some known results for this class or insights about this class. First, if the game was of perfect information, meaning that every player can distinguish any two locations, okay? In this case, actually, we can view this as a single player game with perfect information. We could just see the set of players as one super player, if you want, with the joint actions as the actions of the super player. And then all the theory for single player games would apply for this class of games. So actually, that's not interesting for us, especially that for this latter class of single player games with perfect information, this very strong result that winning strategies exist if only if memory-less strategies exist. So, and this is for a very wide class of objectives called the parity objectives, which subsumes the reachability objectives. It is true that a winning strategy exists for any objective of this class if and only if you have a memory-less strategy. Essentially meaning that if you have perfect information, you don't need to remember in order to achieve objectives. This is a very interesting and also intuitive result. Another result is that if we relax now our constraint on limit on communication, and we allowed without any limit at any point of time the agents to communicate with each other, then they could potentially sort of broadcast to each other at each step what they observe, and then you could collapse this. You can view what they see as one common observation of all the players. You can amalgamate the observations, and then you could view such games as single player games with imperfect information. Again, for this class, we have a result, again, for the same class of parity objectives, that a winning strategy exists if and only if a finite memory strategy exists. And actually, where the memory for the strategies actually is bounded by the size of the game, of the number of locations. You need, in worst case, as many bits as there are locations in the game. So this is also not interesting for us. But the class which is interesting for us, the general class of multiplayer games with imperfect information against nature, actually even for reachability objective, the problem of existence of a winning perfect recall winning strategy is unfortunately undecidable, and this is very bad news. So we have to keep in mind when we do a strategy synthesis. Regarding Georg asks, regarding observable reachability objectives, could you clarify what the potentially win as a member of a coalition without the agent to observe the win? Well, I mean, think, for example, you can change. There are other possibilities to define the notion, but the notion, the way I define it, makes perfect sense. For example, if it's a pursuit evasion game. So if a set of a team of pursuers is chasing one enemy or is searching for some object, then it suffices that this one agent, that one agent actually finds whatever is searched for, and you can say that the team has already won, and we can ignore the fact that, well, later somehow this has to be communicated also to the others, but we can actually say that we have won as soon as we have one of the agents has caught the evader. Okay, good. So now we get to the point of how do we represent higher order knowledge? And actually this notion we define inductively in the following way. So level zero, or zero order, or level zero knowledge would be that what we could consider no knowledge. So this is just what we observe. This is level zero knowledge, is defined by what we observe now. And then you don't need to recompute something, right? Because it's always defined by what you currently see. So the interesting notion is the level one knowledge. And this you can define in different ways, but we we made this choice, our group of researchers made this choice to define as level one knowledge as the most precise estimate that I can make at any given time. My level one knowledge is the most precise estimate that I can make about the current state of affairs. What is the current state of affairs at any point of time? What I can compute from what my initial knowledge was and what I did and what I observed as I did things to the current point. Where am I, right? Where are we? What is the current state of affairs of the whole game? That's my current, that's my level one knowledge. And that's the notion that we take. And you will see later why we picked exactly this notion. While generally the level K plus one knowledge is inductively defined through the lower levels, the level K plus one knowledge consists of my level K plus one knowledge consists of my level one knowledge, first level knowledge of the current state of the affairs, plus what I see as possible level K knowledge of the other players. So for example, if we are two players, my second level knowledge would be my first level knowledge about what is the current state of affairs, plus what possibilities do I see for my partner as first level knowledge, as alternatives. I allow alternatives as possible first level knowledge of my partner. Okay? And I want to again stress this, that you can change this. Level zero knowledge and level K plus one knowledge would stay the same, but you are free to modify the notion of level one knowledge. And this is our choice, and I will explain later why exactly this we picked. So then a level K knowledge-based strategy of a player would be a mapping of actions. For each potential level K knowledge state of mine, what should I do? So every level K knowledge state, possible level K knowledge state of mine should uniquely determine what I should do under this knowledge. Okay, this is what I call the knowledge-based strategy, level K knowledge strategy. And obviously, the existence of a winning strategy, uh, knowledge-based strategy for a fixed level K is decidable. Why is it decidable? Well, because there are finitely many such strategies. We can enumerate them and we can test each of them, and actually testing whether a given knowledge-based strategy of level K on a finite graph can actually be tested in finite time. We can see whether the strategy is winning or not. Okay, it's like model checking if you want. Any questions so far? Okay, so let us, yeah, so about knowledge update. I said that level zero knowledge we don't need to update. With this particular notion of level one knowledge, then I would update my first level knowledge in such a way that if if my current knowledge is a set of locations and I do a given action sigma I, and I make a new observation upon making this action, my new observation is OI, then my new knowledge I can recompute. The most precise, the smallest set that I can compute is the set of all those locations L pri prime that the game can get into, starting from a location in consistent with my current knowledge, and upon a joint action sigma, where my action is this one. In this joint action, my personal contribution is the sigma I. Okay, so all these locations L prime that we can end up in. Okay, this would be my new knowledge. And as we see, this of course will never intersect more than one observation, but hopefully this will be a proper subset of OI, and in this sense knowledge always improves upon what we just blindly observe. I forgot to say on the previous slide that I noticed that with age, I start relying more and more on level 0 strategies. If I want not to forget the next day to take something to work, I put it on the board. I tend to put things on the board to remind me what I have to do with them. So this sort of makes me a level 0 agent. And level 2 knowledge update would then inductively be defined through level 1 knowledge. And we don't have time to go into the details. So let's now come back to our game and ask, so is there a level 0 knowledge-based winning strategy in our example? And level 0 means that the agents have to have a pre-described action just for the given observation. And we know that the first robot distinguishes all locations. So there are two, and there, yeah. So each then the first robot has to be consistent what the robot does in this location bad, and location good, etc. But the second robot cannot distinguish these two locations. So for a level 0 knowledge-based strategy, the second robot has always to pick one and the same action when the second robot observes this bad or good. Okay? And then it's easy to see that there cannot be a winning strategy for profile. Robot 1 obviously has to squeeze when in bad and lift when in good. And the same thing has robot 2, but robot 2 cannot distinguish the two. So actually robot 2 in a level 0 knowledge-based strategy has to pick one action for the observation bad good, but it has to be bad, it has to be squeeze in bad and lift in good. So we see that there is no winning choice for level 0 strategy for the team. Any questions about this? Then the level 1 knowledge, which are set of locations now, for the first robot, nothing changes because the observations anyway were singletons. So there's nothing to improve upon with knowledge. So knowledge here doesn't really help the first robot. So knowing bad, first robot has to squeeze. Knowing good, robot 1 has to lift. But for the second robot, now there's a slight difference because robot uh, 2 might know good or bad, but actually under the knowledge, good or bad, if the second robot squeezes and in the next state, so to say, in the next location, again observes good or bad, the second robot can compute that, but we cannot be in bad anymore. The grip has to be good, right? If this was the observation of the second robot and robot 2 did squeeze and then again observed this, then the second robot can recompute and refine its knowledge and say, oh, okay, but now the grip is good. So actually there are two possibilities for robot 1, and there's now this new possibility of knowing good. And then the second robot will lift. But then the question is, what should the second robot do in good or bad? And you could say, well, then robot 2 should squeeze. But if in bad good it squeezes, then this means that robot 1, in order for them as the team to win, needs to squeeze the first time if the game comes here, then the first robot needs to squeeze in order not to spill, to tilt the cup. But then when the grip is once the grip is good, then the first robot will keep squeezing and will never lift. Okay. So, but if we get now to, so again, no choice guarantees a win. But now if we go to the second level of knowledge, then the second level knowledge of the first robot could be, for example, that the second robot knows that the grip is good and knows about the other robot, the second robot, that the second robot is uncertain. That's a possibility. Or there's a possibility that it knows that the grip is good and that the second robot again is uncertain. But there's also the possibility that the first robot knows that the grip is good and knows about that the second robot knows that the grip is good. Okay? And there are also these possibilities for the second robot. And it turns out that here there is a knowledge-based strategy that actually achieves, and this manifests itself that when both robots know that the grip is good and they know about the other robot, so then they both know that the grip is good and they both know that the other robot knows that the grip is good, then they can lift. Now let me explain this knowledge state of the second robot. This knowledge state means that the second robot is uncertain in both situations. The second robot is uncertain whether the grip is good or bad, but there's a but there is an alternation. The second robot considers two possibilities: that the first robot knows that the grip is bad, and it knows that the grip is good. Okay, so these were knowledge states, individual knowledge states, but we will think of the joint knowledge. So let's consider the joint knowledge state where the first robot knows this and the second robot knows this. Then such a knowledge state would look like this. It would be a tuple of two individual second level knowledge states. And now if we want to interpret it, actually such a view, tree-like view, would be more illuminating. So in this joint knowledge state, the first robot knows that the grip is good and knows that the second robot is uncertain whether the grip is good. And at the same time, the second robot is uncertain whether the grip is good, but knows that the first one knows which of the two is the case. It doesn't know which of the two it is, but it knows that the first robot knows which of the two is the case. Okay? So, and this notion of knowledge trees is closely related to the notion of K-trees, but introduced by van der Meijden a while ago. So then the question arises, how shall we synthesize knowledge-based strategies? And here our approach is the following. We will compute from the game that we have, we will compute another game where the locations of that game will be joint knowledge states. Okay, so there will be states of this type. So in the second level expansion of the game, the locations will have as content such structures, joint knowledge states. Okay, so, and in this expanded game, there we will only be looking for memory-less strategies. Okay, so this is a very important conceptual thing. It's not very difficult to understand, to foresee, but conceptually it plays a big role that you can make this connection between knowledge-based strategies in a game and memory-less strategies in an imagined game of knowledge. So where the locations are joint knowledge states of the players in the initial game. Okay, so this is a very important idea. And for this expansion, the way we constructed this expanded game is we took as a building block, we took a known construction for single player games. And this known construction is the well-known knowledge-based subset construction introduced many years ago by Rife in 1984, which in effect, actually Rife never presented it in this way. Actually, we are the first ones to present it in this way, that actually you can view it as computing level 1 knowledge states of a player, or rather the causality here is in the other way. We took this, what this construction defines, we took as our notion of first level knowledge. And then when we generalized, this generalization was proposed by Edwin Lundberg, my master student 4 years ago. It turns out that the big discovery that he made was that this generalized, so this is the multiplayer knowledge-based subset construction, that you can iterate it. And when you iterate it k times starting from a game, essentially in the expanded game, the nodes will contain the joint level K knowledge of the players. So that was the big discovery of Edwin, that this generalized construction essentially computes level K knowledge of the agents. So I don't know, because of the resolution, whether you see this, but this is the second expansion, second level expansion of the cup lifting game. Okay, and it has six locations, and in each location here we can see the joint knowledge presented as knowledge trees. Okay, of the players. This is the second level knowledge, a second level knowledge state of the first player, and a second level knowledge state of the second player. I showed you actually this node. I showed you some slides ago. I showed you here in this representation. So now we have a whole tree where the nodes are such pairs of knowledge trees. Okay, and then our approach is that on this uh, expanded game, you can now look for memory-less strategies. And when you look for memory-less strategies, you can forget about these trees. When you look for the knowledge, for the memory-less strategies, you only need the identity of these locations. You don't need to know what is inside. This knowledge actually is not needed there when you look for memoryless strategies. But once you find these memoryless strategies, and for this there are existing algorithms, uh, when you find a memoryless strategy here on these locations, then you can present them. Then actually they will define a mapping. Then you can open up these locations, look into what knowledge they contain, and then you would see, then you would obtain a mapping from local knowledge states to individual actions. And in this way, you extract from the memoryless strategy in this expanded game, you will extract a profile of knowledge-based, second-level knowledge-based strategies for each agent to play in the original game. Okay? Yuri asks, 2K appears in the exponent. Does this allude to the expansion of the game results in an exponential increase in the space? Yes, in the worst case, Yuri, this is a subset construction, and in the worst case, it will explode it exponentially. So this will be a double exponent in the worst case. But actually, you have to fight a lot to construct a game where it's really exponential. In many examples, it's much slower, the increase, but in the worst case, theoretically, indeed, these are subset constructions. That's right. So our time starts running up. I just want to say one more very important thing. Then Edwin made a very important and extremely interesting observation that when you iterate this construction on some games, the construction stabilizes in the sense that from a certain game on, applying the construction only returns isomorphic graphs. Isomorphic also with respect to the unobservability equivalences, to the indistinguishability equivalences. This is very extremely interesting. This sort of indicates that also corresponds to that there's some sort of saturation in the knowledge that is accumulated, constructed in the locations. Okay, so basically we get a strategy synthesis procedure. It's not an algorithm because it might not terminate, that you apply this iteratively, the knowledge-based subset construction, you produce expanded games, look for memoryless strategies there. And if you find a memoryless strategy, you convert back these strategies to memoryless strategies in the original game. If you don't find, you can again expand, apply the expansion, and produce a bigger game, look there, etc., until hopefully either you find the strategy or the graph stabilizes. If the graph stabilizes and you haven't found a strategy, then there is no knowledge-based winning strategy for any k, right? That's important. If you stabilize, you can then inductively transfer the result to infinity and say that for no k, there will be a knowledge-based strategy of level k winning the game. Okay, and then we also have some examples that show that this notion of knowledge that I presented may not always be the best choice. So now conclusions. I have many other. So is it semi-decidable in the sense that you might never converge if no strategy exists? Uh, that's true. That's true. That's true, Georg. So I have other interesting theoretical results, but I have to postpone them to a follow-up talk. From what I showed you today, the main conclusions that we can make are that you can take this notion of first level knowledge based on what is the most precise estimate that I can make about the current state of affairs based on what I knew initially, based on knowing the game structure, based on what I see, what happens during the game. What can how fine can I make? What's the finest, or how can I minimize my level of uncertainty, if you wanted to phrase this? And then, based on this notion of first level knowledge, we can define inductively higher order knowledge, okay, by nesting this type of knowledge. And the other important conclusion is that the search for K-level knowledge-based strategies can be reduced to searching for memory-less strategies, but in expanded games, games resulting from this knowledge-based expansion that I mentioned and which I didn't have time to present to you formally. But of course, we have formal definitions and we have characterized it with many theorems. We have studied strategy preservation and so on. In general, the higher the knowledge level, the higher the strategic abilities. As you saw for the example, we had to go to the second level of knowledge in order to be able to solve the games. But for certain games, we may observe this phenomenon of saturation of knowledge, which on the level of the game structure manifests itself that we can get to the point where the knowledge-based subset construction uh, gets to a point of yielding isomorphic graphs, right? Stabilization of that construction. But on the level of local knowledge, you can view it that somehow the knowledge saturates from some point of on, knowing if my level say my level 7 knowledge will not give me more than my level 3 knowledge. Okay, that's this notion of saturation of knowledge. And also that for such games where for these stable games where applying the games does not applying the expansion on it only gives isomorphic graphs, if you have gotten to this stable game, uh, this and you didn't find an observation-based memory-less strategy there, this means that there is no knowledge-based strategy of any level in the original game. So these are the main conclusions. Very quickly, what we are working on currently is this very interesting question. What is actually achievable with knowledge-based strategies? Can we characterize the classes of objectives that can be solved with this type of strategies? Then can we improve upon the existing strategy synthesis algorithms? And we believe that yes, because of the specifics of how our construction is defined. We have already some heuristics that behave better than the current algorithms. What are the structural conditions for stabilization? Can we, can we, by looking at the game graph, can we, based on some properties, structural properties of that graph, foresee that the expansion eventually will stabilize? Adapting the construction by releasing many of these constraints, no communication, no observation, and so on. These are things that we are working on, and we have some results on some of these. Explore other knowledge, first level knowledge representations. Then a very natural question is using knowledge, using logic both for defining objectives and also for representing. There's a very natural, a knowledge-based strategy can very naturally be presented using epistemic logic. If this epistemic logic formula is true, then do that action, etc. So that's a very natural notion that we haven't yet explored. And finally, we have to do a lot of work to solve practical, find practical problems which we can solve with that approach. And then uh, Yuri asked, how about non-exponential expansion of the state space? Yeah, that would be very interesting. Can we find criteria that uh, will structural criteria that will tell us that actually the expansion will not behave exponentially, but only polynomially? That would be interesting. Or other way, maybe also you're hinting at ways of not fully expanding, and there are also ways of lazily just look ahead, expanding only a few steps ahead. There are all of these ideas can be explored. So thanks for your attention. That's what I had to say.